Welcome to This Explainer. Today, we're diving straight into a cosmic mystery hidden beneath reality itself. We're going to explore one of the most profound and mind-bending concepts in all of physics, a puzzle that literally forces us to question the very fabric of the universe and how we understand the fundamental nature of time.
I want to start with a scenario that honestly sounds impossible. Imagine I'm floating safely in space, millions of miles away from any danger, and I'm watching you fall toward a black hole. We're separated by this massive stretch of empty space, and you're just drifting closer and closer to absolute darkness.
At first, everything looks totally normal. I see you moving. I see the glow of your spacesuit. I'm watching you edge towards the abyss. But then, as you get right up to that boundary, a complete visual breakdown begins. You start to look slower and slower. The light coming off of you gets incredibly weak. It visibly shifts to a deep, deep red. And eventually, I literally watch you freeze entirely, right near the edge. From where I'm sitting, I never actually see you cross it. You're just suspended there, forever, fading into a red ghost.
Part 1. The local experience. Something strange happens next, because we really have to ask, what is actually happening to you? Let's shift our perspective away from my safe distance and look at the universe through your eyes as you fall.
Now, what's really interesting about this slide is how it places these two completely conflicting physical realities side by side. Because from your point of view, you don't freeze. You aren't experiencing this endless, agonizing suspension in space. You simply keep moving forward. In fact, you cross the event horizon in a perfectly normal, finite amount of your own time. So how can I watch you fall forever while you have already crossed the horizon?
Did you cross the horizon yet? Well, if you ask this question expecting a single, universal answer, you're going to find exactly where our everyday intuition just completely breaks down.
Part 2. The physics of time. Okay, let's dive into this. To solve this mystery, we have to let go of one of our biggest assumptions about the universe. We have to stop thinking of time as this one, giant, universal clock that ticks exactly the same for everyone, everywhere.
The actual physics here comes down to something called gravitational time dilation. Put simply, gravity changes the relationship between clocks. We actually measure tiny versions of this right here on Earth. A clock on a mountaintop ticks slightly faster than a clock down in a valley. Honestly, our GPS satellites have to constantly correct for this just to keep our phone maps working. But near a black hole, where gravity is unimaginably intense, this effect goes completely extreme. So, from my distant viewpoint, your clock literally appears to run slower and slower.
But something even bigger is happening with the light itself. Remember, I'm not watching you directly. I'm receiving light bouncing off of you. And every signal you send has to climb out of that strongly curved spacetime. As you get closer to the event horizon, those signals get increasingly stretched out and delayed. The frequency of your light drops. A signal you send every 1 second might take 2 seconds to reach me, then 10 seconds. And right as you hit the horizon, that delay approaches infinity. This is absolutely crucial. I really want you to think about this. I am not watching time stop for you. I am watching information about you arrive increasingly slowly. The illusion that you're frozen near the horizon is just that, an illusion. It's entirely caused by the extreme delay of light and information. Part 3. The event horizon. Let's move to the next step and see how this builds. We're going to jump back into your perspective, the falling observer, to figure out what this boundary actually is.
Imagine you're still falling. This black hole is growing massive in front of you. The stars behind you are getting all warped and distorted. The event horizon is right there. You might be bracing yourself, waiting for a physical wall or a sudden flash of light or some kind of cosmic caution tape, but there's nothing. There is no physical, solid surface that you suddenly crash into. Your local physics behaves totally normally. Your own watch keeps ticking at exactly 1 second per second. You literally just glide right across the boundary.
This tells us that a black hole really isn't some giant cosmic vacuum cleaner sucking things in. The deeper description here is pure geometry. The mass of the black hole curves spacetime so severely that it creates an event horizon, which is simply a boundary in spacetime. Outside this boundary, some paths for light can still lead outward, but the absolute second you cross it, the geometry of spacetime becomes so strongly warped that every possible future-directed path points deeper inward. Even light itself cannot find a path that escapes to the outside universe.
Part 4. A deeper reality. But this creates a deeper problem. If you cross the horizon perfectly fine, but I never actually see you do it,
How do we reconcile these two completely different versions of reality?
Let's follow the chain of events here. 1. You smoothly cross the event horizon. 2. You continue your path inward, deeper into the geometry of the black hole. 3. You try to send a message back to me saying, I made it across. But because every path inside the horizon points inward, your message just cannot escape outward. It is physically impossible for the light carrying your message to ever reach me.
And this is where the physics becomes truly strange. I started out by asking what I would see if you fell into a black hole, but the deeper I go, the stranger the answer becomes, leading us right into a much more fundamental scientific question. What does it actually mean for an event to happen? Physics tells us that an event can absolutely occur along your path, even if I, as a distant observer, am mathematically forbidden from ever receiving the information that it happened.
So the crucial point is this. The universe doesn't require every observer to experience reality in exactly the same way. Time is not a universal river flowing through the cosmos at one identical speed. Time is woven right into the very fabric of space-time itself, and because gravity warps space-time, it inherently changes how time behaves and how information travels.
And this brilliantly illustrates the resolution to our paradox. If I say, you never cross the horizon, well, that only describes what I am capable of observing from far away. It's an illusion of the distant view. The reality is that the black hole simply changed the relationship between your physical path and the incoming information I can receive. I am not watching you fall forever. I'm just watching the absolute last pieces of information the universe will ever let me receive from your journey, stretched out over eternity.
You cross the horizon. I never see you cross it. Both mathematical descriptions are perfectly consistent within the laws of relativity. Two perspectives, one universe, no contradiction. It is simply a deeper, far more magnificent geometry of reality than our everyday intuition can easily grasp.
A black hole doesn't just bend space, it fundamentally changes the way we have to understand time itself. If the last information I see of you is frozen, but somewhere beyond that dark boundary, your path continues onward into the unknown, we really have to ask, what else is hidden beneath the geometry of reality? If this cosmic mystery resonates with you, make sure to subscribe to Einstein Vault and join me as we continue exploring the strange and beautiful physics of our universe.